Okay, so for this question, we have monochromatic light of wavelength 441 nanometers, which is incident onto a narrow slit. On a screen 2 meters away, the distance between the second diffraction minimum and the central maximum is 1.5 centimeters. Calculate the angle of diffraction of the second minimum. Okay, so our screen is 2 meters away. Here's our slit. This is 2 meters. Now we have our pattern that looks something like this. So our second minimum, so this would be our first minimum. Our second minimum's up here somewhere. And this distance here is our 1.50 centimeters. Therefore, the angle we can work out, this angle here, we can work out is going to be tan theta equals 1.50 centimeters divided by 200 centimeters. So then we just rearrange that to find theta. And when we do that, we get roughly 0.430 degrees. So that's the answer to part A. Part B, find the width of the slit. Okay, so the mth diffraction minimum is given to us by the equation A sine theta equals m lambda. Now, m in this case is going to be 2, and what we need to do is just rearrange this to find what A is. And when we do that, we get something like we get 1.18 by 10 to the minus 4 meters, which is roughly 0.118 millimeters. So that's the answer to part B. Part C. What must be the ratio of the slit width to the wavelength for a single slit to have the first diffraction minimum at 45 degrees? Okay, so we're going to be using this equation again, A sine theta equals m lambda. It's for our first diffraction minimum. So that means that m equals 1. Now, what we're going to end up with is we want the ratio of the slit width to the wavelength. So we're looking for A divided by lambda, and that's going to be 1 over, it's going to be equal to 1 divided by sine theta. And this is going to be 1 divided by sine 45. And then when we solve that, it's going to be 1.41. So what that means is that we're going to have our slit width has to be 1.41 times our wavelength to have our first diffraction minimum at 45 degrees. And that is the answer to that question.